Right, hello. Today we are going to explore the relationship between differential equations and the exponential equations you find in both nuclear physics and capacitance. How do we set up differential equations? Well, when you have a differential, i.e. a rate of change of something, that is equal or proportional to the thing that is changing, the value of the thing that is changing, you can produce a differential equation. For example, we know that in nuclear physics, that the activity of a radioactive sample is equal to the rate of change of the number of original nuclei. Now, we know the number of original nuclei is decreasing, so it's a negative. We also know that the activity is directly proportional to the number of original nuclei left. The proportionality constant is the decay constant, which is the probability of one decay per second. Now we can see that we have two expressions for activity, so we can equate them. So minus the rate of change of the number of nuclei is equal to lambda times the number of nuclei. Now how do we go from there? We rearrange to get like variables on the same side. So if we divide by n and multiply across by minus dt, we end up with this, which we can then stick integral signs in front of and integrate. What is the integral of 1 over n with respect to n? That is ln n. And the integral of minus lambda with respect to t is just minus lambda t. Because lambda is a constant and is not anything to do with t, we just multiply by t. Mustn't forget our constant of integration. We can then raise e to the power of both sides. So e to the ln n, e and ln cancel, leaving me with n, equals e to the minus lambda t plus c, which I can then expand e to minus lambda t times e to the c. Okay? So we now arrive here, but we have a constant of integration that we need to find the value of. So like with any differential equation, we plug in our initial constraints. So when t is 0, we say that the number of original nuclei is n0. So plugging those values into our equation gives e to the minus lambda times 0 times e to the c. Well, e to the minus lambda times 0, minus lambda times 0 is 0, which is e to the 0. Anything to the power of 0 is 1. So my original number at time t is 0 is e to the c, which I can then plug in to get n equals n0 e to the minus lambda t, which is something you should recognise from A-level nuclear physics. And you might be thinking, oh, but isn't there one for activity as well? Yes. And like we said at the start, A is minus the rate of change of n. So let's differentiate this expression with respect to t. All right? We are going to get n0 remains the same. Any e function remains the same, but it's a chain function, so we are going to multiply by minus lambda. So we are going to get minus lambda n0 times minus e to the minus lambda t. Minuses cancel, leaving with lambda n0 e to the minus lambda t. What is lambda n0? Well, we know a is lambda n, so a naught is lambda n0. So our activity is a naught e to the minus lambda t. Again, should recognise that. If we move over to capacitance, we can produce our capacitance discharging equations. Okay. If we take current as being the rate of change of charge, we know that current, no matter if you're charging or discharging, decreases. And then we have to find an expression for current that involves either Q or T, depending. And so we have to do a bit of manipulation. We know that capacitance is the charge per unit volt. We know that charge is current times time. Okay, so we've introduced current. And we know that voltage is I times R. Okay, well now we've got currents that cancel. So capacitance is T over R, which you can rearrange to get T is equal to RC, which incidentally is where your time constant comes from. Your time constant is the resistance of your circuit times the capacitance. So we also know that I is Q over T, which is therefore Q over RC. So we get two expressions for current. 1 minus dq over dt is equal to Q over RC. Similarly with our nuclear physics differential equation, and like any differential equation, we get like terms on one side. So dq over q is equal to minus dt over RC. Integrating both sides, we get ln q is equal to minus T over RC plus C. Now, C is capacitance, C is also the integration constant. They are separate, they do not mean the same thing. Raise both sides, raise e to the power of both sides, and we get e to the minus T over RC plus C, e to the minus T over RC times e to the C. Plug in our initial constraints. So at T0, we say that charge is Q naught. So Q is going to equal e to the minus 0 over RC times e to the C. 0 over RC is 0. E to the power of 0 is 1. So e to the C is Q naught, leaving us with the equation Q is Q naught e to the minus T over RC. So hopefully what I've done there is showed you just how useful differential equations can be and how we can apply them to A-level physics so that we can see where these equations come from. And if you have a really deep understanding of exponentials and differential equations, it kind of makes a bit more sense. And if it makes a bit more sense, it's more accessible when you sit your exams. So I hope that helps. Let me know in the comments if you want me to cover anything else, in depth or otherwise, and I'll see you around. Cheers.